Good evening. Welcome to People's University Livestream. We're going to continue our science series tonight. Very excited for the physics installment. Before we get to that, just a couple of announcements. This Tuesday, February 16th at noon on Lunch with Books Livestream, the author is Barbara Ellen Smith, and her book is called Digging Our Own Graves, Coal Miners and the Struggle Over Black Lung Disease. It's a book that came out a couple decades ago, but this is a new edition and updated through the present. So that'll be Tuesday. And next Thursday, Dr. Vargas will be back with us to tell us more about physics and her specialty, which she'll probably preview tonight. If you ask a question or like our video or make a comment, you'll be entered into a drawing to win this. And this is just the packaging. Now look how beautiful that is. Heroes of Science. This is Marie Curie. You can read all about her, and there's lots to look at on the packaging itself. I'm not going to take the tumbler out, but it's very nice, and it has her on it. And it happens to be today, I was told by my sister, Dr. Duffy, that it is Women in Science Day, coincidentally. It's not. I didn't plan it that way, but it worked out nicely. So I'm sure that's a highly coveted item. Let's see. Without further delay, Stacey Kefalos Vargas is a professor at the Virginia Military Institute, VMI, in Lexington, Virginia. She received her BS in physics from Wheeling College, yay, Wheeling College, in 1988, and her master's and PhD in physics from the University of Connecticut. Yay, UConn. She joined the faculty in the Department of Physics and Astronomy at VMI in 1996. She was the first woman in science and engineering at VMI to receive tenure and promotion to full professor. She is the recipient of a VMI Distinguished Teaching Award and the Thomas Jefferson Teaching Award. In addition to teaching a variety of physics courses, she performs research in laser spectroscopy. Did I get that right?
Yeah.
Space optics and visible light communication. She has published many articles and received several grants to fund her research. She has collaborated with companies pursuing wireless communication technologies. In 2017, she won the Innovation in Higher Education Award from the Shenandoah Valley Technology Council for her novel research using ultra-short pulse lasers and free space optics communication, which sounds very cool. Passionate about her teaching and her research, she lives in Lexington with my friend Albert, her husband, and their 5 children. And again, happy Women in Science Day. Stacey, here is Stacey Kefalos Vargas.
Okay, thank you, Sean, for that introduction. And I'm honored to be here tonight to talk about physics. And I was told, I'm going to share my screen here. I hope this is working. Okay. I was told for this lecture, we wanted to talk about the fundamentals of physics. So I promised a journey from Newton's laws to Albert Einstein if we get enough time. So I'm going to take off with that now, and we'll see how far we get. So I have to confess that when I signed up to do this, I forgot that I would be teaching physics without math. So this is sort of me up here stressed in the corner when I realized that I was going to have to do this. So I'm really going to try my best to limit the number of equations. I do have to sneak in a few, I think, to cover some basic concepts of physics that we would cover in an introductory physics course, obviously minus all the math. So I'm kind of teaching in a foreign language tonight. So with all that, I would say, my goal is really to make you think, teach you maybe something new, and hopefully inspire you to learn more, because this is just touching on topics, and I think there's so much more to learn about each of them. So hopefully you'll be inspired to learn some more. Okay, so we're starting with classical mechanics, and classical mechanics
we often in because we're not seeing your PowerPoint.
Oh, you're not seeing it again?
And
Oh,
it worked
shoot.
fine in every test we did.
Okay, hold on a
I knew
second.
this was going to
Let me
happen.
see. Let me see. Hold on. Where are you? Hold on. Here you are. Let me see. Share screen. Share screen. Try again. Okay.
There you go.
Let's see if we got it now. We got it now?
Yes. Go ahead and run your show and I'll make sure.
Okay. So you didn't see anything so far?
No, go back to your beginning.
Okay. I'm going to start with
Do a
this.
quick
Okay.
start.
So this is what I was saying and that you couldn't see apparently. Let me hide this. Okay. So I'm teaching physics without math. So I'm kind of teaching in a foreign language. I'm glad you can see my slides now and not just have to stare at me talking. But I really do hope that you'll be inspired to learn more as we talk about these concepts. So classical mechanics, like I said, I was starting classical mechanics, deals with the macroscopic world and how we describe motion in a macroscopic world, meaning things that we can see with our naked eye. This is also called Newtonian mechanics because Newton was really responsible for most of the laws that describe the motion, although there were many people that gave him the information to be able to write the laws. But he sort of gets all the credit in calling it Newtonian mechanics. So to start off, if I was doing an introductory course, we would start off by just talking about motion, nothing that causes the motion, but just motion in general. So I have a picture here, and I don't know why I have a dog driving a car, but a dog driving a car. And if we wanted to describe the motion of that car, I might say, how fast is the car moving? And you might say, well, 55 miles per hour. And then I might ask you what direction the car is moving, and you might say east. But if I ask you for the velocity of the car, you would have to tell me 55 miles per hour east, because the velocity term incorporates both the speed and the direction. So instead of taking 2 steps to describe the motion, I would just say the velocity is 55 miles per hour east. And so the point being that you and I might describe the motion a little differently depending on the terms that we use. And so let's talk about that in terms of distance too. So we talked about the velocity. Now let's think of a baseball player. So I've got a baseball player here in the corner and he hits a home run. And I might ask you to describe that motion if he runs from home plate back to home plate. And so you might say, well, knowing the distance between bases, he runs 360 feet. But I might say, well, his displacement is 0. And the reason I would say his displacement is 0 is because displacement is defined as the change in position. So if the runner started at home plate and if the runner stopped at home plate, then the runner's displacement would be 0 because they start and stop at the same position. So you might be describing a total distance in that motion, but I might be describing the displacement. And so you get 360 feet and I get 0. So the point, again, is how we describe motion of an object is very important and can be different depending on who's describing the motion. And later in the talk, we'll realize where the person is relative to the motion. So we're going to keep all this in mind. So in an introductory course in general physics, we would spend time talking about these terms and ways to describe motion. So I would introduce terms like displacement, which we just talked about as the change in position, the velocity, which we talked about, which is sort of the change in position over time, but giving me a speed and a direction, and an acceleration, which is a change in velocity over time, also with a direction. So we could use this information to describe a car moving down the highway, a runner running, an object falling vertically, anything that was one-dimensional motion. We would take time to use the equations. We would do it with equations, but I'm not doing it with equations tonight, to describe the motion of the object. And that would get us through one dimension. But if we wanted to go to 2 dimensions instead of just 1 dimension, say a football being kicked over here or a diver diving, maybe for whatever reason you want to slingshot a bird, right? So in these cases, the motion has not just 1 dimension in X, but it has a Y and an X. So it has a horizontal direction as well as a vertical direction. So this makes things a little more complicated, obviously, than just looking at motion in one direction. And in these cases, we call this type of motion projectile motion. And so really Galileo, and there's a lot of great history. If you like history, you should read this Era of Science, really interesting. Galileo really should have more credit for coming up and initiating the idea that once an object is in the air, it doesn't matter what the mass is, it will experience the same acceleration. So we are going to talk about this projectile motion. We're going to neglect air resistance, as did Galileo, so neglecting air resistance. And we're going to say once our object is in the air, the football that was kicked, or a baseball thrown, something dropped, any of these cases, once an object is in the air, the only acceleration it experiences is acceleration due to gravity. And this is a constant acceleration. And gravity really was solidified, the idea of the constant acceleration, by Newton. We define acceleration due to gravity, G. I'm sorry, I'm introducing some numbers here. G is 9.8 meters per second squared, or 32 feet per second squared. But what's most important is that gravity is always pulling down. Okay, so when you get up in the morning, this gravity is always going to be pulling down. And this is sort of the idea that Newton had when he watched the apple, supposedly watched the apples fall from the tree. And so we want to take this now and think about it a little more. Once an object's in the air, this projectile or something that's dropped, we say that the object's in free fall. And again, we're neglecting air resistance. So an object dropped or a projectile fired will all be what we call free fall. And the reason we call it this is because the only acceleration it's going to experience is the acceleration due to gravity. So once that object is falling straight down, gravity keeps the acceleration due to gravity pulls it down. And this gets kind of interesting when we look at a projectile, right? Because if I think of, say, maybe a bullet or something being fired in the X direction, if the only acceleration that's acting on this object is down, then this horizontal velocity really shouldn't change. Okay, so the gravity is acting down, but this horizontal velocity, once it leaves this bullet launched or gun, whatever it's leaving from, this velocity is not going to change. And so basically what goes up still has to come down, all because of gravity. So if I think about that velocity vector for this soccer ball that gets kicked and goes along sort of this projectile motion, if I think about the actual velocity vector, it's going to have a horizontal velocity. It's going to have a vertical component to the velocity. And if I follow that vector motion for the velocity, there's nothing that's going to change about the x velocity. So if I follow the x component, the horizontal part of the velocity, right, it's going to be the exact same value throughout the motion, because the only acceleration that I have that can affect the object is the acceleration due to gravity. So in fact, the y velocity starts decreasing because it's trying to go up. Gravity keeps trying to pull it down. And you get to a certain point here, which you're at the top of the ball's at the highest point, the y velocity goes to 0, but the x velocity is still the same as it was initially. So the projectile keeps going along in that x direction, but now the y velocity starts pulling it down to the ground. So it was trying to go up, eventually it reaches a 0 vertical velocity and then goes back down. So this is all projectile motion. Once the object's in the air, the only acceleration it experiences is acceleration due to gravity, which always wants to pull the object down. So once we spend some time talking about motion, trying to learn about motion in one dimension, motion in two dimensions, then we have to talk about what causes the motion. And so far, our discussion has really been limited to velocity, acceleration due to gravity. Now we want to introduce forces, which are what actually cause the motion or make the object move. Okay, so this is where Newton is really going to take over with his 3 laws of motion. Okay, so we want to go through and talk about each of the 3 laws of motion. So Newton's first law, it's sometimes called the law of inertia. And I'm just going to read it out. It says an object in motion will remain in motion with a constant velocity unless acted on by an outside force, or an object at rest will remain at rest unless acted on by an outside force. So a simple example would be sort of a shopping cart, right? So if you walk into the grocery store and there's a shopping cart sitting there, it's not going to all of a sudden start moving for you to go down the aisles, although maybe eventually with AI it could. But for now, if you go to the shopping cart, it's just going to sit there unless you push it. So if you start pushing on it, as I do here in the picture, then I can move the object. So by applying a force, the object will move. If I don't apply a force, the object's not going to move. And so that's what Newton's law basically tells us. An object at rest is going to remain at rest, as it does here. An object in motion is going to remain at motion at a constant velocity unless it acted on by a force. So once I start pushing it, if I push on it with the same force, it's going to keep moving with the same speed. I can stop it by letting up on the force, or, if I bang into something in the store, then there's going to be a change because another outside force will be applied. So this is really Newton's first law, or what we call the law of inertia. And inertia is really related to mass. I like to think of it sort of as a measure of the mass, but it's in formal terms called the tendency of an object to resist the change in its state of motion, or resist a force. So if I think of the shopping cart empty, then it's going to have a certain inertia. And then if I fill it up, it's going to have more inertia. So it's going to require a bigger force if the shopping cart's full than it would if the shopping cart were empty. And so this law of inertia is the Newton's first law. And inertia is just that tendency of an object to resist the force. Okay, so what about Newton's second law? Newton's second law talks about the acceleration of an object is directly proportional to the force acting on the object and inversely proportional to the mass. So you might know this as F equals ma. In the way it's described here, it's the acceleration is directly proportional to the force, and inversely proportional to the mass. So if I think about that in terms of me pushing on the shopping cart, if I apply a certain force with nothing in the shopping cart, I'll get a certain acceleration. But then if I fill my shopping cart, right, I increase the mass and I still apply the same force, then I'm going to have a much lower acceleration. So as I add more mass, then I start having a lower acceleration unless I increase the force. So F equals ma is how we normally think of it. The force is directly proportional to mass and acceleration. But the more mass I put in here, then the more force I'm going to have to apply to make it keep moving if I want the same acceleration. And Newton's second law can also be related back to Newton's first law, because if the net force is zero, then the acceleration has to be zero. So if there's no net force, again, then I go back to zero, and that's sort of what we already said in the first law. Okay, so now on to Newton's third law. Newton's third law says for every action, there is an equal and opposite reaction. So if you went and for whatever reason decided to push on a wall with your finger, the wall is going to push back on you with the same force. So there's an equal and opposite reaction as you push on the wall and the wall pushes back. Or if you think about being in a boat and you jump out of the boat, if I jump out of the boat, then the boat's going to go in the opposite direction. And so this is the action. The boat going in the opposite direction would be the reaction. So this is Newton's third law of motion. Okay, so now once we know F equals ma and we know a little bit about gravity, now is a good time to think about weight, or the weight of an object, and how weight differs from mass. So mass of an object is not the same as weight. And the mass of an object is always the same. But the weight is a force. And that force can actually change because the acceleration due to gravity can eventually change. But let's talk about the weight in general. Weight, by definition, if we say it's a force, right? F equals ma. So weight is the force. M is your mass. And the acceleration in our weight equation is just the acceleration due to gravity. So W is equal to mg, okay, where g is that 9.8 meters per second squared in the case where if you're on the Earth's surface, and we'll talk more about that in a few minutes. But weight in general is mg, and it's really a force, and it's different than mass. Your mass is measured in kilograms if we're in MKS units, and it's not going to change. But this really leads to another law that Newton also came up with. So let's talk about the law of gravitation. So Newton's law of gravitation, or of universal gravitation, I should say, says for every object in the universe attracts every other object in the universe with a force that varies directly to the product of their masses and inversely proportional to the square of the distance between them. And so again, this is where I have to introduce equation because I think it makes more sense in an equation form. So the force, there's two masses here, and there's going to be a force between these two masses. And the force between those two masses is equal to the m1 times m2. So I multiply their masses and divide by the distance between them squared. Okay, so G is a constant factor. So don't worry about the G. It's just a universal constant, and it would just be a factor in there. The point is that every mass attracts every other mass. So if I'm here at M1, M2 is going to attract me toward it. If I'm here at M2, M1 is going to attract me toward it. And this is true for any mass. This could be me and you. This could be the Earth and the moon. So Newton really laid out this foundation that for every body, every object that we have, there is this attractive force between any two objects. The bigger the distance is, right? The bigger the distance is, the smaller the force is going to be. Okay, so as you get really far distances, then that force is actually going to decrease. Okay, it's going to decrease. So for every object that in the universe, this is true. It can be bodies, heavenly bodies, it can be people, it can be any object. Okay, so let's talk then a little more about gravity, and let's look at the force of attraction between you and the Earth. Okay, so this case, we have our two objects, M1 and M2. And I should note that if your object is really big, like the Earth, we think of all the mass being concentrated at the center. So we always measure our distance from the center of the Earth to the other side. So we measure our distance from the center of the Earth. So in this case, if I have Superman standing on the top of the Earth, the distance between Superman and the Earth would just be the radius of the Earth. So I'm going to take this all here and put it in my equation. So G is a constant. The two masses are the Earth and Superman. And the radius is the distance between me, the Earth, and Superman. So just the radius of the Earth. That would all be the way I would calculate weight. So really, I could calculate the weight of Superman if I knew his mass. The mass of the Earth is a constant. The radius of the Earth is constant, and so is G. That's all equal to weight. And we also know that that's the Superman's mass times G. So actually, we can use this universal gravitation equation to calculate G, which we said was 9.8 meters per second. And in fact, if you put in the G, that constant, the mass of the Earth, the radius of the Earth, and you calculate that, you would find this number to be 9.8 meters per second squared. So anywhere on the Earth's surface, this G is going to be 9.8 meters per second squared. Okay? So, and it's kind of funny, I'm talking to my computer, I can't see anything. I'm used to either Zoom where I see a bunch of students looking at me, or a classroom where I see a bunch of students. So it's kind of odd. I feel like I'm in my office talking to myself. So let's take Superman and move him somewhere above the surface of the Earth. Okay, so let's take Superman. Instead of Superman being on the surface of the Earth, I'm going to move him to some height above the surface of the Earth. So what's going to happen to this acceleration due to gravity up here? Or what's going to happen to his weight when he's way up high above the Earth? Well, if we just think about our equation, when we're on the surface of the Earth, that radius is just the distance between the center of the Earth and Superman. But now I also have to add, if I'm way up here, I have to add the height h, right? So it's not just the radius of the Earth, it's the radius of the Earth plus this h value. And so it turns out if you divide something by a bigger number, right, the number is going to get smaller. So I might have 9.8 down here, but I'm going to have less than 9.8 up here. So Superman is going to weigh less as he gets further from the surface of the Earth. And so would you. So if your ambition is to weigh less, you might consider changing your altitude, right? Go to some higher h value above the surface of the Earth. But all this universal gravitation allows us to calculate G. It allows us to calculate weight and anything associated with our weight. Okay, so far, just talking about motion and Newton's laws help us describe the motion in this macroscopic world. Velocities, accelerations, projectiles, all those good things. And now we know a little bit about Newton's universal law of gravitation, which tells us about, standing and why we're standing on the earth. Our weight is always pulling us down. But previously, when we were talking about motion, I mentioned that when you talk about motion, how you describe it can vary. So I said the baseball player running around the bases has a displacement of 0. And you might have said the baseball player runs 360 feet. This can also happen when we look at motion from different locations or reference frames. And so we need to clarify a little bit about the difference between an inertial reference frame and a non-inertial reference frame. So let's think about what we're talking about here. So basically what I'm saying is what a person on a train thinks is happening on the train is one thing, but what a person standing here outside the train observes might be different than what is actually observed on the train. And so we want to figure out, how do you talk about this? In order to talk about relative motion, we have to define this inertial and non-inertial reference frame. And so if I talk about inertial reference frame, an inertial reference frame is one in which Newton's laws apply. Newton's first law, his law of inertia, applies. So remember the law of inertia. The law of inertia was when we talked about the shopping cart, Newton's first law. And we said that the object at rest remains at rest unless acted on by an outside force. So in the case of an inertial reference frame, that law has to hold. If that law doesn't hold, then it's a non-inertial reference frame. And so we want to think about these difference between these two so we can describe them. So we can safely assume for our purposes that anything fixed on the earth is an inertial reference frame. If you're in your house, you're in an inertial reference frame. If you're standing on the sidewalk, you're in an inertial reference frame. Or if you're in an object moving with a constant velocity, you are also in an inertial reference frame. So as long as your velocity is constant, you're not accelerating, you're not changing your velocity, then you're in what we call an inertial reference frame. And Newton and Galileo were really on to relative motion and really knew about relative motion. We really think of relativity when we think of Einstein because he sort of solidified it for all of physics. But there were ideas of this relativity long before. Okay, so let's think about what is a non-inertial reference frame. In the case of a non-inertial reference frame, any accelerating reference frame is a non-inertial reference frame. So if you remember in the last slide, I said it had to be a constant velocity. If it's an accelerating reference frame, then it is a non-inertial. So a simple example, we'll look at some examples to distinguish between the two. So in a simple example, I might have my sunglasses sitting here on the dashboard. If I'm driving my car at a constant velocity, nothing's going to happen to my sunglasses. They're just going to stay at rest there on my dashboard. Oops. Okay, they're going to stay at rest here on my dashboard. And so if I'm driving along and then I accelerate, if I go around that turn or do something really fast, then the sunglasses are going to go sliding, somewhere across the dashboard or off the dashboard. Once I accelerate, I'm no longer inertial reference frame. And you can see that because we've violated Newton's first law. These sunglasses should be at rest, and they should stay at rest unless they're acted on by a force. When I accelerated around that turn, there was no force acting on the sunglasses, but the sunglasses moved. And so that accelerating reference frame is no longer an inertial reference frame because it violates that first law of Newton. Okay, so let's think of another one. Another example of a non-inertial reference frame, an inertial reference frame. If I'm in a roller coaster and I'm going up the hill at a constant speed, then I am in an inertial reference frame. Newton's law holds because I'm sitting there and I'm stationary. Nothing happens to me. So Newton's first law applies to me fine. But once I start to accelerate and zip down the hill, right, what happens? I go flying back in my seat. And as I go flying back in my seat, there's really no force acting on me. It was that accelerating reference frame that allowed me to go back in my seat. So I'm no longer obeying Newton's first law because there's really no force acting on me, but for whatever reason, I go flying back in my seat. So this is the difference between an inertial reference frame and a non-inertial reference frame. Anything that's accelerating is a non-inertial reference frame. Anything at rest or moving at a constant velocity is what we refer to as inertial reference frames. Okay, so now we can talk a little bit about Newtonian relativity, and I'm talking now not about relativistic effects that we'll talk about with Einstein, but these are just simple Newtonian relativity that Galileo and Newton sort of knew about. And so what it says is basically Newton's laws of motion should hold as long as you're in an inertial reference frame. Okay, so as long as my reference frame is either stationary or moving at a constant velocity, then I should see the laws of physics obeyed. Of Newton's laws of physics, I should say, the 3 laws of motion should be obeyed. And so we can think of a simple example here. If I'm riding in my car and for whatever reason decide to take a coin in my hand and drop it. So imagine yourself in the car, not outside the car, but actually in the car. You hold your hand out, you drop the coin. What happens? Right? The coin should fall straight down to the floor. Right? So if you're in the car and you decide to drop your coin, that's what you're going to see. You're going to see the coin fall directly to the ground. Okay, and so that obeys Newton's laws. F equals ma. The force gets gravity pulls the coin to the ground. F equals mg in that case. It all obeys, and Newton's laws are obeyed. And so this would be an inertial reference frame, and the laws of physics would hold. What happens if instead of being in the car, I'm outside the car? So I'm standing here and I'm watching the person in the car. I see the person in the car holding the coin and dropping the coin. But in this case, when I see the person holding the coin, in my reference frame, since the car is moving, the coin is actually moving, right? So what I'm going to see is that the coin's going to have an initial velocity, similar to what we saw in that slide way back, right? Where if I can go back and then forward, I think I can. I'm going to see something along the lines of this, right? So on my coin, that the person observing already has an initial velocity in this direction. So in fact, I should see something like this projectile motion. And so, in fact, that is exactly what happens. So if I'm standing here, the car's moving at the constant velocity, I see the coin in the person's hand. It has to, in my reference frame, an initial velocity. So what I see isn't the coin go straight down. I see it as a projectile. But that still obeys the laws of physics that I should see because in my reference frame, that coin had an initial velocity. So in both cases, the laws of physics should hold true. And so I see the projectile motion, and in fact, that is what I see, and that's what happens. So Newton and Galileo really knew about relativistic motion in terms of inertial reference frames, as we see here, and Newton's laws holding in those inertial reference frames. Okay, so classical mechanics, as we talk about it here, Newtonian mechanics, really allowed scientists to explain a lot about objects in motion. And it also formed the basics for how we study things like fluids. There's buoyancy forces, again, forces that come into play that we can use Newton's laws to analyze, why something floats, why something sinks. It also helped us analyze wave motion. If we look at a particle on this wave, we can still talk about its velocity, its acceleration, the distance that it moves, and we can analyze that motion under the laws of Newton's laws of motion. And so classical mechanics was really a foundation in the macroscopic world for all the concepts that we study in a general physics class in, I would say, the first semester. The second semester of a general physics class, we moved to electricity and magnetism. And so James Clerk Maxwell developed a lot of theories about electricity and magnetism. And he really studied sort of how electricity and magnetism were really waves in nature. And when he was doing his research, he found that these electromagnetic waves had a velocity. And it turned out that that velocity was equivalent to the speed of light. And so he didn't mean to show that electromagnetic waves were light, but he sort of came to the conclusion because when he solved for the speed of his electromagnetic wave, it turned out to be the speed of light, which is 3 × 10⁸ meters per second. And in fact, he found out that it was made from this constant, this mu and epsilon naught, the permittivity and the permittivity and emissivity of free space. And so if you multiply those, take the square root, 1 over it, you end up with the speed of light. And so when he realized this, he also realized that in a vacuum anyway, the speed of light should be a constant. And so this led to a lot of confusion, because now this concept of relative motion, what happens if you have a light source that's moving? And so how can you have a constant speed if the light source is moving? You should have this sort of kind of thought process like we did with the coin. When we dropped the coin was moving initially in the reference frame, then it had a projectile motion to it. So how could we have this constant speed of light? And so this is where Einstein started to do a lot of his research and theorize about electromagnetic waves. And there's a lot of really good stuff out there about how he imagined himself riding on an electromagnetic wave and what he would see. And so it's really, again, interesting history if you like that to read about. But this really led us from the late 1800s into the early 1900s, led us into what we now call the era of modern physics. So it was in the early 1900s, I would say, or late 1800s, we started to transition from this classical physics of just Newton into the modern physics era with Einstein. And so Einstein had this special theory of relativity, and he proposed this in 1905 after thinking a lot about this fact that the speed of light had to be constant. And so he developed this special theory of relativity. We call it special to separate it from the other theories. And it's built upon what was already known in those cases of relativity. But he had to somehow incorporate the electricity and magnetism and the laws of the electricity and magnetism that Maxwell was determining in his theories, and the fact that the speed of light was constant. So what Einstein came up with was sort of two postulates that go with the special theory of relativity. And the two postulates for the special theory of relativity are that one's called the relativity principle. And it says not just that Newton's laws are the same in any inertial reference frame, but that all the laws of physics, and that included the laws of electricity and magnetism, had to be the same form in all inertial reference frames. So if I'm in the car moving at a constant velocity, or if I'm watching the car moving at a constant velocity, both of us should see all the laws of physics the same, not just Newton's laws of motion. It had to incorporate the laws of electricity and magnetism. And I chose not to go into a lot of the detail of electricity and magnetism. One, I wasn't sure if I'd have time. And two, I don't know how to do that without math. So I don't go into those theories. But Einstein realized that they had to apply in these inertial reference frames. And then the second postulate was this constant speed of light, that light has to travel through empty space with a speed of 3 times 10 to the 8th meters per second. And it's in a vacuum, we say, independent of the speed of the source or the observer. So it didn't matter what reference frame you were in, the speed of light had to be a constant. And as did any fundamental physics constants, had to hold true in any reference frame. And that was really a distinguishing factor when he came up with this relativity, was the fact that that speed of light was constant. That's really what transitioned Einstein to create this special theory of relativity that said the principles had to, all laws had to hold, and that the speed of light had to be constant. And so with special relativity, there are some odd consequences. There are, with special relativity, the fact that time and simultaneous events in time get sort of confusing. So it turns out that time, in the case of special relativity, depends on the observer's reference frame. So we really, in Newtonian physics, think of time as an absolute. Like, it doesn't matter where I am, whether I'm in the car, whether I'm on the ground. In all those cases, I just have time, t, period. That's it. I just know the time in either of those. But what Einstein said was that time is really dependent on the space you're in. So if you are an observer on the ground, you sort of have a clock on your wall in your reference frame. If you're an observer out in space somewhere, you have a clock on your wall in your reference frame. And so time was not an absolute. Time was dependent upon your reference frame. So I like to sort of think of a clock on the wall as you're standing on the sidewalk and a clock on the wall as you're moving in some spaceship. It doesn't really matter except for when you're getting to speeds that are close to the speed of light. So really, special theory of relativity, or what we call special relativity sometime, really isn't a big deal until you're traveling at speeds close to the speed of light. And so we sort of bring space and time into sort of one quantity. Space-time, Minkowski was really a mathematician, but did a lot with this space-time. And if you've watched any sort of visualizations of special theory of relativity, you've probably seen some of these space where they try to give you four-dimensional space, where they show you, okay, here's space, and then the fourth dimension is time. And these sort of intimately related, space and time. And so there are a couple of odd consequences that go along with that space and time. And one of them is what we call time dilation. And again, this doesn't matter except for when you're moving at speeds close to the speed of light. So you're not going to see time dilation here or moving in your car. But if you think about a spaceship that maybe could travel at the speed of light, there's something that we call the twin paradox that we try to use to sort of describe this and what happens. If you have two twins that are on Earth and one gets in a spaceship and travels at the speed of light way out somewhere and then comes back, the clock in the moving reference frame moves slower as observed by the person here. So the twin here on Earth is going to see that clock move slower. And as a result, when he comes back, the theory is he would be younger. The twin would be younger when he comes back from space. So that is something that we call the twin paradox. And it's what we call time dilation. So if you were an observer on Earth and you're watching what's going on, as something traveling at the speed of light out there, then that clock on the traveling spaceship is actually moving slower in your reference frame as you see it. Is moving slower. But again, remember, as Einstein said, the clocks are different. If you're out in the spaceship, you're not seeing anything different because your clock to you is just the clock in your reference frame and it's your clock on the wall. So it's not moving slower. Okay, and the other odd thing that happens is something that we call length contraction. So if you are on the ground observing something moving at the speed of light, then what you would see is that the length of that object starts to get smaller. And the closer it is to the speed of light, so if you're not really close to speed of light, you're not going to see a change in your spaceship like this. But as your percentage, if you're like 0.86 times c, 0.95 times c, 0.99995 times c, in each of these cases, the length of the object that you observe would be getting smaller. And you might think, well, these are really bizarre effects, and why does relativity matter to you? They actually, when you use your GPS, the way the GPS works with the satellites out in space, they had to incorporate relativistic effects so that they could make sure that they were really calculating distances and times correctly with the GPS. So yes, Einstein's relativity should matter to you every time you use your GPS, and this incorporation of how time and length are affected when you go close to speeds of light. So I'm probably finishing before I should finish. Maybe we'll have some questions. But I didn't know how much I should try to say in this talk at a level that would be fundamental physics. But I hope I gave you a little bit of insight into classical mechanics and the motion in the macroscopic world. Newton's 3 laws of motion: object at rest remains at rest unless acted on by an outside force, or an object in motion remains in motion unless acted on by an outside force. F equals ma, which is probably one that you already know. And for every action, there's an equal and opposite reaction. And then obviously the universal law of gravitation, which allowed us to look at gravity at different heights. So every object is attracted to every other object with that force that's proportional to the masses and inversely proportional to distances. Talked a little bit about inertial reference frames. An inertial reference frame is a non-accelerating reference frame. It's either stationary or moving at a constant velocity. And then the non-inertial reference frame is an accelerating reference frame. So in this case, we looked at the case of a roller coaster going down the hill, right? Or the sunglasses shooting across if I went too fast in my car. And Newton and Newtonian relativity talked about how Newton's laws were applicable in any inertial reference frame. But Einstein, after learning about electricity and magnetism and the speed of light being constant, came up with the special theory of relativity and those two postulates that all laws of physics had to hold in an inertial reference frame, and that the speed of light had to be constant, as do all other fundamental physics constants must be constant in any reference frame. And there's a lot more to learn. Very interesting history. If the science piece and just the math and everything doesn't appeal to you, you might consider some of the history of that era from classical mechanics and definitely in modern physics. We'll talk a little more about that next week when we get into light and how light behaves, because it kind of continues on into the modern era of our analysis of light as a particle or light as a wave, and how we can treat light and its behavior. So we can talk a little bit about lasers next week, and how we treat light as waves and particles, and then a little more into some of the research projects that I've worked on. So in end, I just want to thank Sean and the People's University, and I hope that you had the opportunity to think a little, learn something new, and maybe I've inspired you to learn some more. I hope. So at that, I'll turn it back to Sean in case there's any questions. Like I said, I might be finishing a little early.
Yeah, actually, you're perfect.
Am I? Okay. Let me see if I can get back to you, or should I leave my PowerPoint up?
No, I took it down, so go ahead and close it.
Okay, let me close it.
Hear me on the screen.
Okay.
Yeah. We loved your visuals. A lot of people commented.
Oh, good. I kind of, yeah, fun stuff, right?
Afraid of copyright with Superman, but the guy had yellow on, so I'm not.
Yeah, he wasn't really the real Superman. So sorry.
Yeah.
Yeah.
Let's go over some of the questions.
Okay.
Here's the first one we had.
So the acceleration will change, right, as you get higher from, or as you increase in altitude, because the value of g changes. You won't notice that, because if you remember in that denominator, it was the radius of the Earth, which is really big. So even if you got to twice the radius of the Earth, then you would weigh 1/4 of what you weigh. So it would have to be a really huge distance, but there would be a slight change in your weight, because there would be a slight change in g. So it might not be 9.81, maybe it'd be 9.809 or something. So we slight change. Yes, you would.
Your mass is the same.
Depending on the height of the altitude that you were at.
We had this comment. I'm sorry, I encouraged some here's one as well. What do you think about that question? I think that's.
Does a radioactive cat have 18 lives? Well, so I don't know about a radioactive cat having 18 lives, but I will say there's a famous experiment called Schrodinger's cat.
Yes.
And so in that experiment, that is sort of introducing the idea and concept of quantum mechanics. And the idea is that you take a box and you put a cat in the box, and you put a radioactive sample in the box, and you close the box. And the theory says that, is the cat dead or alive? And you don't know if the cat's dead or alive. If the radioactive sample goes off, then the cat dies. But you won't know that until you open it up and look. And once you open something up in the world of quantum mechanics and take a measurement, then you've changed the object. And so there's this Schrodinger cat experiment. Is the cat dead or alive? And you don't know until you take a measurement, and then it's not really fair. So,
right.
So I don't know about the radioactive 18 lives, but I know about Schrodinger's cat.
Open that box, you've exposed yourself to radio.
Yeah, this is true too, and you might die.
I said this, by the way. So
I'm disturbed by the idea of it. Well, in an accelerating reference frame, right? They may not hold, but this is where Einstein comes in with his general theory of relativity and sort of analyzes accelerating reference frames, and that's where you get into the idea of mass and this space, time, and mass sort of changing space. So these large object can change space, and you can talk about gravitational waves, because there's these changes in the space-time, then we get gravitational waves. And I don't know how much people follow science, but this LIGO, which is this huge interferometer, were built. Two of them were built in Washington State, I think, and then somewhere, maybe Texas, I forget now, where they can measure these gravitational waves and have in fact detected gravitational waves. So there's this whole other field that we can't get into, but that does talk about these accelerating reference frames and space-time and general relativity.
Very cool. Well, let's get into the meaty questions. Ready?
Okay. Is string theory a subset of classical mechanics? String theory is more in quantum mechanics, and I am not a string theory person at all, so I can't tell you a lot about string theory. I apologize for that.
That is a bummer.
Yeah.
I think most of us were here for string theory.
Yeah, right.
Here's another one. How about wave particle?
Wave particles. So next week, I'm going to talk about the wave particle duality for light. And so they said for electrons, I think about it for light because I deal mainly with photons, not so much electrons. But the concept is the same. And with light, what we'll find out and see next week is that light can really be treated as a particle or a wave. When light interacts with matter, we can treat it as a particle. And when light's doing things like interfering or diffraction, then we treat it as a wave. So you can actually treat light as both states as with electrons.
How cool is that?
That's really cool. And actually, we find out later by de Broglie that everything has a wave nature. So you too, Sean, have a wave nature.
Oh, yeah.
If you noticed that, yeah.
Wave, but I have a wave.
Yeah, you have a de Broglie wavelength.
And speaking of me, I made this joke.
Tom Brady.
And let's see. Mary Ellen made an even better joke. Football humor. I'm sorry.
Football. I like football humor. I should have done football. I did baseball and soccer, but yeah. I did have a football being kicked.
Mary Ellen made this comment.
Yeah, time dilation is kind of crazy, right? I mean, I think it's easier to understand than length contraction, but time dilation is definitely odd. But it's a little easier for me to think about in terms of visually. If I they always show this example where if you took like a mirror and shine light sort of as a clock almost, and thought about every time the light goes from one mirror to the other, that's a second or something. So if I'm watching it in my own reference frame, I see the light go up and come back, right? But if I'm looking at the spaceship that's traveling at the speed of light, I see the light go up and come back. It's sort of an arc because the spaceship's moving. And so the time actually takes longer, right? Because the light has to go up and here down. So that to me is a little easier. That length contraction is much more disturbing to me.
It's all mind-blowing though, really.
Yeah, yeah. There's a lot of really good stuff out there on relativity.
Let's see.
I like the humor. We have to have good humor.
You have right?
Gotta have good humor.
Bonnie has a compliment for you.
Oh, that's very kind. Thank you. I'm glad you could follow.
And Liam, who loves physics,
enjoys learning about inertia and acceleration. Ah, very good. Well, yeah, no extra. Yeah, maybe.
And here's another compliment from Aaron.
Oh, thank you. Very nice. Aaron's talks were great. I mean, chemists do really great things. I mean, we're talking about forces and masses. Aaron's talking about bonds and excellent stuff.
Well, that was the question that started the whole thing, right? So when does chemistry become physics?
Physicists say that physics rules all, right? So we like to think that physics is the fundamental science, of course. Yeah. So when does chemistry break off on its own? I don't know, right?
There you go. Fair enough. Yeah. Any other questions? We're going to draw the winner of the Mercury tumbler right here very soon. So if you have another question, you better ask soon. All right, here we go. I'm doing it this way. My lawyer isn't here, so hopefully I don't get in trouble. Here we go. Dave Wren is the winner.
All right, Dave Wren. We got some WJU people out there.
Yeah.
Thank you for watching. He probably just asked and then left, right?
I don't know, but he was the winner of our trivia contest. Yeah, there he is.
Is he there? Okay. It's the Tumblr radio. Oh gosh, I don't know why everybody made things radioactive. I didn't make things radioactive. I guess Madame Curie did.
Aaron is admitting that physics rules.
Does rule.
There you go.
Yeah, yeah. I mean, people get intimidated by physics often because people are afraid of math, and you shouldn't be afraid of math. You should just embrace.
He won beer. Okay. Bonnie says I missed a question. Can you re-ask the question, Bonnie?
Oh, she submitted another one.
Let me take a look.
Hopefully it's not another string theory question.
No, it wasn't. I'm scrolling back up to see what I missed. Meanwhile, maybe she'll type it back in. Oh, no, that was the one we showed you.
We answered.
Mm-hmm. Perhaps you can sing a song while I do.
Me? I don't think so. Can talk about more physics. I really do think it's very interesting history of that whole era. I think people should, if you're interested, read about that, because as in the modern era too, the whole thing with Einstein and this arguing that was going on about how things behaved, and even with Newton, because Newton really has a lot of ideas, but they're built upon other people's ideas, and it's kind of neat to go back and look at the other people that gave him all those ideas.
There you go. Well, I couldn't find her questions.
Okay.
Next time, but we're going to give her the last word, which is that theology rule.
Well, I can't argue with that. That's what was going on in all these eras, right? They were kind of fighting with what God was. People were saying God said versus what science said, but we know that can be together too. But at the time,
it's Galileo saying, nevertheless it moved, something like that.
Yeah.
Yeah.
Yeah, and that's how it all started, right? Studying the heavenly bodies. That's how science started, right? They were all looking at heavenly objects and how they moved.
Right.
Yeah. Yeah.
Stacey, thank you. That was wonderful. Thank you very much. And we're looking forward to next week when you have the...
Yes, we'll talk about light, waves, particles, and lasers, and some science.
There you go.
Yeah.
Tune in next week, folks. Bonnie will ask her question, and I'll have a few of my own.
Okay.
See you then.
All right. Thanks, Sean. Thanks, everybody.
Thank you. Thanks, everyone who attended. Bye now.
Thanks.